So as we have the last section of our volumetric changes which can happen, we saw the changes that can happen in solids, in liquids. Now we are going to be dealing with the volumetric change in gases. We are going to actually see the major difference from the two that we had. Yes, when we dealt with the liquid or with the liquids, there was some differences that we dealt with, considering that there is a container, there is a liquid inside of the container. Now, as we have the gas or the gases that we have, it's not about the container. Yes, the container can be there, but it's not about the container. It's about the gas on its own. It is affected by temperature and pressure at the same time. So gases are affected by what? Temperature. That is the temperature and pressure. The major part that we have of the pressure, it is because they are compressible. Because gases are what? Are compressible. So if they are compressible, therefore we must consider temperature and what? And pressure. So meaning to say, our volumetric change, as we consider the part of volume, we shall be considering volume, relating it to pressure, relating it to temperature, as we deal with what? With gases. And also, we do not have those length area, guys. Yes, just volume. So there's nothing much that I can add. That is what we can see in this case. I want you to just go through maybe some of the basics of gas, like thermodynamic of gases. And also it is important for you to understand this because it is going to be our continuation of our power machines, N5, this part of our gases. So we are going to consider quickly. Let us move on to the gas laws. So the laws that govern as we deal with gas, or as we deal with what? With gas. So all gases obey three laws that relate to volume and pressure, and also temperature, because remember, volume, pressure, temperature. So they follow the three laws, which is all of them, they follow these, all right? Which is one, that is the Boyle's, guys, the pronunciation is in your hands, guys, all right? Number two, then that is Chaucer's law, all right? Then we have got the pressure law. We also have the pressure law, which is from this guy, which is Gay Luskas, like this. So guys, you end up even biting yourself trying to pronounce these people's names. So you see, guys, in Africa, we need also names that are to be taken. A Zulu name as a theorem or as a law, a Sotho name as a law, as a theorem. This must happen in Africa. You need that. Because now, guys, you look now, we pronounce, and these people, they were clever, very, very clever. They name these laws after their names or surnames. They just, okay, I'm the one. They put the name. Nice. They do not put another name which can be used so that at least the pressure law. They want the name must. So guys, I just know these are people's names that we are talking about. So do not even worry about that. You can even Google them. And if you Google, you can search about them, understand more about these people, which have these laws that are giving us headache today. So I'm just saying, guys, but this is important, guys. Africa, we need also the best out of us. If we had same, maybe it is the effect is on the language barriers to say, in this region, there's this language. In this region, there's that language. In that region, there's this language. In this region, there's this language. So if there was a universal language for Africa, I think maybe it was going to help in development of many things, many things. But now we have the opportunity because of the English that is used like almost everywhere. So meaning to say, guys, these laws, they must be generated from us and so on. So guys, let me go straight to what I'm talking about here. All right, number one, we had the Boyle's law. It's the guy who is Robert Boyle, that is Robert, who in his lifetime period was studying about the relationship, what is happening when the gas is there, the pressure, volume, what is actually happening. So he ended up observing that the pressure of a gas is inversely proportional to its volume. On a condition now, it did not end there. So you see, these guys, what they do, this one is putting this one. These guys, they were just cheating us. Not like in terms of not knowing. The first person works with temperature being constant. Another one works with another thing being constant. Another thing being constant. Then all those things are being combined together. So it was just a funny thing about these laws. Anyways, let's talk about this part. So the Boyle's law is stating that the pressure of gas. So guys, you can pronounce better. I don't know, guys, how you're going to pronounce this one. As for me, I just did. These are people's names, guys. As for me, guys, if it was something, I don't know, but let us just have this way. So the pressure of a gas is inversely proportional. It is inversely proportional to its volume. You just need to understand the concept there. To its volume, provided the temperature, the temperature remains constant. Remains constant. So when something remains constant, it means there is no change in that. There is no change in temperature. T1 is equal to T2 is equal. If there are phases or stages, temperatures are the same. Temperature remains constant. T1 is equal to T2. We are going to notice something later on. That's why I was saying some of these things, guys, it was just like I do not know, because we are going to talk about the gas processes where we talk about the three basic gas processes which are in our syllabus, and we shall be talking about a condition where we have got isothermal process, an isothermal process where we say the temperatures are the same. So you see, we go back to the same thing, but here we are dealing as a law. So a law, guys, it is just like if you go back to your mathematics, you are dealing with exponents, laws. You just need to know a law, what it states, and the formulas under that law. You are done. It is like, what can we say? It is like a cramming part. You just need to know about that law. You're not the one who started that law. So you just have to observe what that person was observing during his time. So this is what he observed. So therefore, we can say that pressure is inversely proportional to the volume, or we can say volume is inversely proportional to pressure. So meaning to say, if we had a constant, if we had P is equal to a certain constant, let's just say K over V, if we cross multiply this one, it follows that PV is equal to what? To K, where K is a constant. So this is the part. Remember, there's no temperature there. So PV is equal to K, meaning to say we can rewrite this PV, which is equal to K in this manner. So P1, V1 is equal to the second stage, P2, V2, which is equal to this constant. So that is the idea or that we are referring to. So you equate it to the constant, but as for just revision's sake, I just want us to have it this way so that we can understand. So if there are three stages that are happening, remember, we're talking about the gas expansion from point 1 to point 2, originally to the final. So it can even expand to another stage again. So 1 simply denotes initial values. Whenever I put 1, I'm talking about initial values. Whenever I'm going to use 2, I'm going to represent final values. Final values. So that is the condition. So PV is equal to a constant, or VP is equal to a constant, since temperature is the same. So the typical questions that we can be given, guys, like I said, is a direct part. Just know the law, then answer questions. Do not worry about much, guys. All right. So on this question, it's an example which can be used. A 500 cubic centimeter cylinder with hydrogen gas has a pressure of. Calculate the pressure of gas after the cylinder volume is increased to, meaning to say there is a change from this volume to this volume. Take note. We are given the first part, the volume corresponding to what? To the pressure. The second one, they want you to calculate the pressure after when the volume is V2. So the pressure that they want you to calculate is P2. That is the case that you can be given. It's only that they did not mention that provided that the temperature. But when you are given this information is just pressure and volume, you know that the formula that is pressure and volume is this one from our Boyle's law. So meaning P1 V1 is equal to P2 V2. What is our question? To calculate P2. So we're simply going to divide by what? By V2 both sides. So that's it. So meaning to say, therefore, P2 is equal to this P1 over P2 over V2. So that's it. P1 V1 over V2. Let's just substitute our P1, 220 Pascal. There's no kilopascal there. All right, times our V1, which is 500, over V2, which is 900. Just like that, you substitute. So I was supposed to take my information properly, but it's just like direct. Anyways, that was going to give us 122,22 pascals. This is what we have. So questions can be of this nature. You relate to the information, to the formula where you have got what? Volume. So that is the condition. So in this case, there's temperature there, meaning to say we cannot talk about that one. All right, so this is the first law, and some of the other things that I erased it there, put them into consideration as well. Let us move to the second guy, who is called Jacuz. Is it Jacuz, guys? I don't know how to call this one. Chaus. Chauses. So it was Chaus. So this guy came up now with his law, which is the Chaus's law. So it's Chaus's law. Guys, the English, this one, it's gonna make us to end up biting ourselves. Anyways, so in this case, this guy discovered in his observations, he concluded that The volume of an ideal gas is directly proportional to the absolute temperature, provided pressure of the gas remains same. This one is talking about what? Pressure remaining the same. All right. So the volume is directly proportional to, so the volume is directly proportional, proportional. This is proportional, is directly proportional to the absolute temperature, to the absolute temperature. But it is not just like that. It is on a condition. It is on a condition. On which condition? Provided that. All right? Provided that the pressure of gas remains the same, remains constant. So when there is no change in pressure, provided the pressure here, provided the pressure, P1 will be equal to P2. That is what it means. P1 is equal to P2 is equal to P3. So in this observation, it follows that, therefore, we are saying volume varies directly, this is what you are given, guys. This is a law, take as it is. V is directly proportional to what? To temperature. So V is equal to, provided that you put a constant, it's going to be KT. So V is equal to KT, where K is the constant. So we can divide by T so that we do know our constant. So dividing by T both sides, it follows that the constant is equal to V over T. So therefore we can say V1 over T1 is equal to V2 over T2 is equal to V3 over T3. That is what we can say, since volume varies directly proportional, to T. So we saw that if you introduce a constant and do this, therefore V1 over T1 is equal to V2 over T2, just like that. Just like that, which is equal to a constant. So this is what I just want you to take. Yes, we can write is equal to a constant for the sake of revision. So like I said, 1 for initial, 2 for final values. And take note, your temperature in what? In Kelvin. So your temperature in Kelvin. You are dealing with the absolute temperature. Let it be in Kelvin. Always try to understand, guys, working with Kelvins, because that's your power machines. That's your power machines. You're going to be working Kelvin. So know that. All right. So this one, we talked about this, guys, to convert to Kelvin from degrees Celsius. You just add 273. Your answer will be what? Will be in Kelvin. So that's it. Let's consider this question. An expandable container contains this volume of gas at this temperature. So we are given the initial value of volume 2,4 cubic meters at that temperature, at the initial temperature of 25 degrees Celsius. So convert to Kelvins. If we add 273, that was going to give us 298. All right. Calculate the volume of the gas. If the temperature is increased to this value, we have got the final value of the temperature. Add 273 here. That was going to give us 343. So the question is, we are supposed to calculate the final volume. We do not have this. So which of the formulas is that we have? We are not told about the pressure. We're not given that. It means it is a constant value. So we go back to this. V1 over T1 is equal to, you're done. So V1 over T1 is equal to V2 over T2. Just take your information. You're done, guys. We want to find V2. How can we remove this T2? We just multiply by it. Since it is in the denominator, multiply by it both sides. So therefore, the V2 that we want is equal to this, T2 times V1 over T1, just like that. So substituting into this formula, we were going to have the value of V2. Our T2, 343 times V1, 2,4 over T1, which is 298. So that is what you are going to have. So our V2 was going to give us, as we have got our volume, as we have got this one, it was cubic meters. So our answer is going to be also in cubic meters, 2,762 in what? In cubic meters, just like that. So that's how you answer these questions under exam condition. Look for the formula which is best to answer the question that you're given there. All right. So that's it about this guy. Let us move on to another one of the pressure law. So number 3, we have got the pressure law. All right. So that's our number 3, which is from Gay Lusask. So this is Lusask, okay, law. So that is the pressure law, this one, the pressure law. So guys, next time I'm just going to write the formulas. This saying about this law of this one. I'm just going to write the formulas, guys. You now know these laws because I might pronounce the way that you don't even like. Maybe you've got a better way. All right. So this one, it was from the guy who was called Joseph Louis Gay Lusek. All right. In his stages of life, he saw that in the working of the gases as a final observation, the pressure of a given mass varies directly with the absolute temperature of the gas when the volume is kept constant. This one is talking about volume kept constant. That's why I was saying, guys, we are talking about 3 things here: temperature, volume, and pressure. This one is saying this is constant. This one is saying this is constant. This one is saying this is constant. You see, it was like, I don't know if you understand me. But anyways, that is what you have in your textbook. So you must learn it. So pressure, let's write it down. Pressure of a given mass. Pressure of a given mass varies directly. So it varies directly with the absolute temperature. Absolute. All right, with the absolute temperature of a gas. When the volume, that is the condition now, when the volume is kept constant. So this is our condition now, when the volume is kept constant, meaning to say the volume is not changing. V1 is equal to V2. So understanding this is going to help you when we deal with the gas processes, because we're still going to go back to this part. When V1 is equal to V2, that's an isochoric process. We're going to talk of these now as processes now to say this is now gas process, which is called the isochoric process. Only that we shall be adding some of the gas laws. Here we are just talking about the law focused on a person. Only that. So meaning to say from this guy, P is directly proportional to what? To temperature. So introducing a constant, it means P is equal to KT. So we can divide by T to have a constant. So meaning to say our constant is P over what? P over T. So P over T, if it is equal to constant, therefore P1 over T1 is equal to what? P2 over T2, which is that constant. So this is the whole idea of the pressure law. So let us just have it here. So therefore we can just conclude that P1 over T1 is equal to P2 over T2. That's equal to the constant. So this is what we can have in consideration. P varies to the temperature, and temperature is in Kelvin. From these guys, your temperature in what? In Kelvin. So that is how we answer these typical questions. Let us consider this question. We are given air at atmospheric pressure. The air that is given is at atmospheric pressure. What is the atmospheric pressure? So we are given P1 initially, as our atmospheric pressure. Remember, that's 101,325 Pascal. Or you can have it in kilopascal as kilopascal there, 101, that. So this is the atmospheric pressure. It is at that pressure and at this temperature. So add 273 to convert to the Kelvin. That was going to give us T1 of 298 Kelvin. In a coffee drying chamber is heated by steam heating tubes. What is the chamber pressure when the air reaches 135 degrees Celsius? So add 273. That's our T2 was going to be 408 Kelvin. So the question is, what is the pressure at this temperature? What is the value for P2? So as we can see, this time we are dealing with the pressure and what? Temperature. So that will be the best formula to work with. P1 over T1 is equal to P2 over T2. You work with the formula, guys, that is best there, with the information. So concluding this, we're going to have P1 over what? T1 is equal to P2 over T2. So what we need is P2. So let us remove T2, multiply by T2, both sides, that was going to cancel. So therefore our P2 is equal to what? It is equal to this one, which is T2 408 times P1 over T1, our P1. All right, so if you use this value, it means you are going to have it in Pascal. If you use kilopascal, your answer will be in kilopascal. So if you use this value, no problem. Let me just use it 101,325 over what? T1 298. So that is going to give us P2 in Pascal, which is 138,726,846 Pascal. Guys, we can even convert to kilopascal, divide by 1,000. It was going to give us 138,727 in kilopascal. We can have it that way. So that's our P2. Just like that. So these questions can be obtained that way. It's a matter of playing around with the law. As we can see, it's a direct thing, guys. I don't think it's going to be difficult, guys. This one is a direct. So the last thing is to combine all these three laws together. Let us try to combine them. Remember, right? So combining the three, let's try to do that. Combining all three. So if we combine these three guys together, let's see. The first one was saying, okay, let's go back to the first one. Our Boyles was saying P1 V1 is equal to P2 V2. The second one was saying V1 over T1 is equal to V2 over T2. The third one was saying P1 over T1 is equal to P2 over T2. So let's combine. As we can see, here P1, all right, P2, P2. These are already in the numerator, because this is like over 1, this is like over 1. They are already in the numerator. So we've got P1, which is equal to P2. We're not going to repeat this part. It is already in the what? In the numerator. We go to the V1. There's V1 here, V2. Here there's also V1, V2. Don't repeat, just write as it is. So they are also in the numerator. So that's V1. This is V2. T1 and T1 in the denominator. So this is T1 here. This is T2, T2, like that. So as we can see, it's going to be like this. What is in the denominator, let it be there. In the numerator, it maintains in the numerator. You just combine them together. So this is what you can have. So when you are given a condition where they give you volume, pressure, temperature on the same question, you combine your laws. You combine them together. Then we gonna also have the gas processes. That will be another class that we are going to consider, which has got the issue, or I mean the idea of gas processes. We are going to, I mean, the characteristic equation of a gas. We are going to do that one as the last class. But for this one of combining these three, let's consider this example here. It can help us to answer that question. If we check this question clearly, they gave us, in this case, the volume of a given mass of a gas at this temperature, and the pressure is, they gave us the volume at those conditions. So V1, this volume of 40 cubic meters is occurring, or we are having it initially when the temperature is what? When the temperature is 30 degrees Celsius. So add 273. That's, we have got T1 there, all right, which is 303 Kelvin. And a pressure of, there is also a pressure. So they gave us all the three. 0.2 times 10 to the exponent of 6 pascals. They never gave us a condition like this, where all three are happening at the same time. It is either they were giving us these two, or they were giving us these two, or they were giving us these two. But yet they gave us everything for the first condition. Then they are asking you to calculate the volume of the gas at this temperature and this pressure. These are the second condition now. So from that, we need to calculate V2. We do not know. But the temperature is what? -12. Add 273 to convert to the Kelvin. That was going to give us the value of T2. If we add 273, it was going to be 261. So T2 is 261 Kelvin. And the pressure is given, P2 as 0.6 times 10 to the exponent of 5 Pascal. So as we can see, all variables are there: volume, temperature, pressure. This is the best formula, which has got everything. So from that formula, we can use it and manipulate to find our V2. So it gives us, or it tells us that P1 V1 over T1 is equal to what? P2 V2 over T2, just like that. So we want to find V2. So you must remove this one, P2 over what? T2. If you wanted to remove T2, this one, in the denominator, what are you going to do? You are going to multiply by T2 both sides. What about if you wanted to remove P2? You were going to divide by P2. You were going to divide by what? By P2. So that's it. This one was going to cancel. This one was going to cancel. You're remaining with what? V2. So that's it. So V2 is equal to this. T2 over what? P2 times that other part. So this is it. What do we have here for T2 over P2? So T2 is given, this is it here, our T2, 261 over P2, as it is 0.6 times 10 to the exponent of 5 times this part, P1 V1. So that's P1, 0.2 times 10 to the exponent of 6 times V1, which is 40. Take note, it's cubic meters, so our answer is going to be in cubic meters, all right? Everything over T1, and our T1 is 303, just like that. So this was going to give us the value of what? V2, which is the final volume at those conditions of the given temperature and what? And pressure. The volume that was going to correspond was 114,851 in cubic meters, as we have this one in what? Cubic meters. So that's how these questions can be given. So you have to work out as many questions as you can as an individual. Try to figure out how these questions can be given as. So like I said, our next class, we shall try by all means to work on the characteristic gas equation. All right, so make sure that you become part of membership so that you do not miss any of the other classes that we are going to be having, as we shall be working on all introductions of topics and trying to do question papers. So if there is a section which is not complete, guys, the comment section is there. Let's communicate. I might not answer your comment at that moment, but I will go through those comments to see which playlist that we are supposed to add videos. So let's do that so that we can finish all sections and other subjects for N4, where you see that there is a missing part. Let's communicate. And for those who are under membership, let's also communicate if there are questions that we feel like these ones, they are still giving us a headache or a challenge. Let me know about that one so that we can have those questions done on our membership section. But for now, that is it, guys. Till we meet again.